To introduce our induced EMF in terms of electric fields, if we've got an induced EMF, it is going to be due to a changing magnetic flux. So our induced EMF equals negative d phi dt. Our particles are going to feel a force that is Q times our electric field. So that induced EMF implies that we're going to have an electric field tangent to this loop as it's drawn in the picture with those orange arrows, and that these charges are going to feel a force that's Q times our electric field, and that we're going to see that as an electromotive force. Okay, so the work done by this electromotive force in moving an electron or a charge one trip around this circular loop is going to look like the work done by that force in one trip around, so 2 pi times r. And that work that's done, we could say, is that charge moving through a potential difference, which is given by our electromotive force. So if we compare both sides of this equation, that's saying that our electric field is related to our electromotive force and that path, that 2 pi r around the circle. So we want to compare that to our flux, because we want to compare our flux and our electromotive force to our electric field and our electromotive force relationship. So our flux, as long as we're perpendicular, we can just use the B times A. And in this case, with our perfect circle, we have pi r squared for our area of the loop. So if we compare this and add it all in there, instead of EMF in our electric field equation, we're going to use the negative d phi dt. And we've got negative 1 over 2 pi r d phi dt. And in this case, that simplifies to negative r over 2 and dB dt. So how our magnetic field changes with time, because we're not going to change the area with time in this case. So what we come up with when we take this is that our EMF is going to be given by the closed path integral of our path dotted with our electric field, which in this case, they're in the same direction. So that would be a simple multiplication, but we're going to take all these little DS's around our loop. And that path dotted with the electric field is a line integral. So in other cases, our electric field might not be constant, or the path is not perfectly circular. So this leads us actually to a general form of Faraday's law, where we have this closed path integral around our electric field gives us the negative d phi dt, so the negative change in magnetic flux. So that is our induced electric field. And it's good to note that that is not a conservative field. So if it were a conservative field, a closed path integral would give us a 0, but we don't get a 0, right? Because we're getting this changing magnetic flux, which is inducing an EMF. So our induced electric field is not conservative, which means it acts more like friction than like some of the other fields we've used, or some of the forces we've used. Okay, so you have an example in your book as well that's the electric field induced by the changing magnetic field in a solenoid. So in this example, you are given that your solenoid has an alternating current. So the current changes from some maximum to a minimum value, and the current's actually a sinusoidal function, right? So in this solenoid equation, we want to start out with our general form of Faraday's law and do two different things with it. So first of all, we want to switch our d phi dt in terms of what we're given here. So we're going to use the equation for phi of BA cosine theta. So the cosine theta has to do with the angle between our magnetic field and our area. You can see we're going to choose a path of integration that's described by this blue loop. That's going to have a normal direction in this direction, which also happens to be the normal direction of our area and the direction of a magnetic field that would be caused by this current loop, right? So that cosine of theta, we can just turn into a 1. The area, again, describes the area where the magnetic field exists. So the area where the magnetic field exists happens to be the area of our solenoid. So they give us that the solenoid has a radius of capital R, right? So in our solenoid, the magnetic field looks like mu0 times a lowercase n, so remember that's the turns per unit length, times an I. So mu0 times n, and in this case they give us that our current is changing with time. So our current looks like I max times cosine omega t. So when we want to do how is this changing with time, we've got to take a time derivative of this b, right? Our area is not changing, but our b definitely is. So this becomes pi r squared mu0 in I max. Those are all constants. And then we need to take the time derivative of cosine omega t. And omega is just the radial velocity. So it's telling you that it's changing so many radians per second. That's how fast our current is changing. So I max, and we're going to take a derivative of cosine. So what we're really going to get is a negative sign. We need to get that omega out there. But that negative sign is going to meet up with this negative in front of our derivative, and they're going to cancel out to a positive. So we've got, on the right-hand side, our changing magnetic flux being all these constants, omega, sine, and you know what? I dropped a thing. It should be sine omega t. I dropped a term. So that's a sine omega t. All right, so that's our right-hand side of the equation. It should equal the left-hand side of the equation. So it should equal E dot ds. So in this case, we picked a path that is a circle just outside our solenoid. So we picked a path that should be in the same direction, so our dot product should just become a multiplier. And again, I don't need that line up there. So our magnitude of E times 2 pi r should equal this stuff on the right-hand side. So pi r squared mu0 n, which is our turns per unit length, I max omega sine omega t. Okay, so just taking it one step further, what we are going to come up with, and I'll write it in a different color, is that our magnitude of our electric field is going to be this stuff on the right-hand side here divided by 2 pi r. So in this case, it's mu0 times n times I max omega r squared 2r on the bottom there, and then sine omega t. And that is for when we are outside the solenoid. So if you look at the example in your book on page 949, when you are inside the solenoid, again, so if I look at the solenoid end on. If we are inside this solenoid, where R is less than R, let's give ourselves some labels. So where our radius is less than the radius of the solenoid, this is the only area that is contributing to our flux. And so you're going to use a lowercase r in your flux equation here. And you are going to get a slightly different equation for the electric field inside the solenoid versus the electric field outside the solenoid. We'll pause there and pick up with generators and motors for our next recording.